The previous broadcast, I was talking about the problem that we were working on, and the problem that we were on, let me back it up a little bit, we were actually working on this problem, and the problem that I wanted to do using Excel is problem number 2, which is this problem right here. And I've got a little scribbling here. I'm going to actually sort of get rid of this to sort of show you where we're at now. What's going to happen is I'm going to actually use Microsoft Excel to calculate all of these things that I had you do the table for in class, because I really want to motivate you later on in the year to start using Excel. And if I just said, hey, use Excel for this problem, you'd have no reason to. So what I'm going to do is I'm actually going to do this problem on Excel to show you how great a tool Excel is for solving problems. So kind of seeing this problem done in under 10 minutes is a really great motivation to sort of get it going. So on Excel, I'm going to construct the table that they asked for here. And of course, in the sheet that you actually have in class, you don't just have a table of angle, initial velocity, hang time, and distance. This is labeled as horizontal distance. And I believe I had one more choice or one more thing on there, which was height. And you're going to organize all these answers. So in other words, on Excel, we're going to make a table of angle, initial velocity, hang time, horizontal distance, which I'll call range. So again, just to be kind of clear here, when we say horizontal distance, we're referring to range, and then finally we have height. So we're going to actually calculate this in Excel. And I want to kind of remind you that we have some formulas here. So for hang time, the formula that we derived is that's going to be V naught sine of theta divided by G for the time going up. And then we double that to get the total hang time. And then for the range, we're going to have X equals V naught squared times the sine of 2 theta. And that's divided by G. And then for the height, we're going to end up getting V naught squared sine squared theta all over 2G. That's the height. So we're going to actually plug these formulas into Excel. And there's going to be a way for us to generate a table starting from 5, 10, 20, 30, 40, 45, all the way down to 85 degrees. And Excel is going to fill in all these values for us. And that's what we're going to do. So let's get to it. So I've got a spreadsheet here. And you know what? I'm going to zoom in a little bit just so you can kind of see what's going on. Let's zoom in, say, 125% magnification and see what that gives us. So that looks pretty decent. Now first, let me label some letters here. So I'm going to have V naught. I'm going to have gravity. And here's the problem with Excel. Excel works in radians, and I want to work in degrees. So this is also an incentive to pay attention in your trig class and learn this distinction between degrees and radians. So I'm going to put a thing here that I'm going to call radians to degrees, so RTOD. And I'm going to actually write some numbers in. So we're told that we have 15 meters per second as our speed. That's actually stated in the problem. Gravity, of course, we know is 9.8. And this radian to degrees, this is a conversion factor that converts radians into degrees. And the way you convert that is, well, actually, the proper term is degrees to radians, since that's actually what we're working in. So I'll just call it D2R. D2R. So, or D2R. So degrees to radians, that conversion ends up being, you take pi, you divide it by 180 degrees. And that'll convert any angle to radians so that Excel can read it properly. So now let's go ahead and let me just go back to the sheet here that we were working on. So I'm going to actually type in this whole table, and then I'm going to use these formulas. I'm going to use this to get hang time, and this to get range, and this to get height. So let's go ahead and do that right now in Excel. So I have the angle, I have the initial velocity, I'll just call it V naught. And make sure I have these right. First it's, yes, hang time, then range, then height. And you know what, just to make sure that I have enough room for you to see everything that's going on, let me just take this and lift it up a little bit. All right, good. So now my angles are 5 and then 10. And here's the interesting thing. Excel's so quick, I can actually do all of the angles up to 85 in increments of 5. So even though the problem says go by 10 degrees, we're going to do all these. We have 15 meters per second as our initial velocity next, and we just labeled. So I've got these variables here. I'm going to go ahead and name these so I can use them as letters in the problem. So let me just go ahead and name them. So excellent. So that's good. And let me just name this guy. Excellent. So I'm going to add one more. I'm going to add G, and that will label B2. Excellent. Whoops. And whoops, one more to add. So we'll call this, yeah, there we go. And we got it. So we're all good. So now, V0 is going to, let's just check this. Should be, there we go. So let's go and fill all those in as V0. Now the hang time. What I'm going to do is I'm going to actually calculate it from the formula. So that's going to equal V0 squared times the sine of, now I need 2 times my angle, which is 5 degrees, times this conversion factor I'm going to be using. That whole quantity, whoops, I'm going to divide all of that. Oh, that's not the hang time. The hang time is actually, make sure I got that right. Oh, wrong formula. Whoops, so let's just correct that. That's going to be 2 times V0 times sine of my angle, which is 5 degrees, times that conversion factor. That whole quantity, and we're going to just divide that by 9.8. Excellent. And you know what I want to do is, let me just take this to be 3 decimal points. So like that, I narrow it, clicking up here. And now, this is the cool part. I can now fill this in for all these angles, not by recalculating, but by clicking and dragging. Now, let's do the same calculation for the range. So that's going to end up being V0, and we'll square it, let you see that better, times the sine of, and again it's going to be 2 times my angle times my conversion, so that whole thing, oops, and then I'm going to divide that by 9.8, like that. So, and again, let's take it to 3 decimal points, like that. We go ahead and fill that in, so we get every single one of those. Finally, let's go ahead and do the height. So this is the beauty of Excel. So the height is going to be V0 squared sine squared theta over 2g, so that's going to be V0 times the sine of our angle theta. I might have said 2 theta. I meant to say sine of theta times our conversion factor. And we divide this whole quantity. So that's the thing. Now we square it, and we divide it by 2 times g. And that's our answer. And again, let's take it to 3 decimal points like this. And we click, drag, and fill in. And this is just perfect. So that's our whole setup right there. So what we've done is we've actually calculated this table in a matter of minutes. Now, let's go here and take a look at what the next problem says. And the next problem says we want to graph the horizontal distance versus time. Or sorry, versus angle. So let's go ahead and do that. So the way I'm going to do that is I'm going to take this thing, click, and drag it so that it's over here. Whoops, didn't mean to do that. Because I want to actually plot the range, not the height. So I'm going to plot this range versus the angle. So I'm going to highlight these 2 columns. I'm going to click Charts. and then I'm going to click scatter. And then click one more time. And this generates this beautiful graph right here. I can actually drag it down a little bit lower to just kind of separate it from the numbers. And we see that there's this weird pattern of when we plot these. So this is a plot of the range for various different angles. So these are angles down here. And it looks like we get the same horizontal distances for two different angles in each case. So let's go back and look at our numbers. This is kind of interesting. So when we do that, if you notice, let's see. Here we get a range of 3.987 for 5 degrees and also for 85 degrees. Let's just kind of look at that. So 5 and 85, they're the same. Let's see. I get 11.133. Sorry, I get a range of 7.853. 7. Let's see. Let's check those out. So let's make those blue, and we'll make this blue as well. So 85 and 5, 80 and 10. Let's try one more. Let's make these 75 is 10.71. Sorry, is 11.48. 11.48 for 15 degrees. So if you notice the trend here, what it seems to be based on these numbers is that in general, the relationship between angles that yield the same range, they add up to 90 degrees. So that's, memorize this fact. It's going to be on your exam. I can't remember where, I don't remember how, but I remember that we wanted to test on that. So get that memorized. And of course, the legwork is doing all this work that you did in class. Now, when given a choice between two angles that yield the same distance, which is a better one to use when punting a football in a football game, I would imagine you want to use the bigger angle. Because then the ball spends longer in the air because it goes higher. And then, I don't know, I guess your players have more time to catch it. I'm winging it here. I played chess in high school, so I have no idea. So, yes, this is where I'm just overstepping my authority and just trying to talk a good whatever. But I'm talking like a theoretical physicist, and if I'm worth anything is, trying to predict reality from the basis of equations, it would seem to me you'd want to kick the thing higher in the air. Just because you get longer time in the air and then people have a chance to run and catch up to it. But I don't know. That's the best I could come up with. So that's it for that one.